I think on Thursday I'm going to have you do a Desmos activity, one of those card matches. And what you're going to be given is graphs of original functions in color. I think they'll be in red. And then graphs of their derivatives in blue. And then what Paige is going to do is try to match the proper graph with its derivative graph. So not dealing with functions, but graphs. For some people, this is the easiest thing we do all year. It's very visual. You don't have to do any actual math. Other people struggle with this because it is so visual. There's nothing I can tell you to do. Like if Paige is struggling with this, all I can tell her is you're looking at slopes. What are you looking at? Slopes. All right. So up here, and you might, this is from our book. I screenshot it. That's why it's got these 39 to 42 on it. These are the graphs of functions where, whoops, y equals f of x. Go ahead and write that on there. The y values are the functions evaluated at x. We're going to match them down below with their derivative graphs. So down here, these are graphs where the y values represent the derivatives, which remember are the slopes. So it's a little tricky because you're thinking of slopes being plotted. So I'm going to start with the very first one up here, number 39. If I were to hop on here and say, what's the slope of the tangent line at 1? What would you say? 1, right? How about right here? What's the slope of the tangent line? 1. How about right here? 1. The slopes are 1. So the derivative graph would be where y equals the slopes equals 1. So take the word slopes out. It's the graph y equals 1. Does that make sense? Which one do I match it with? B. Go ahead and write that. So that's B. All right, that one was fairly easy because the slope was the same everywhere. This one's got varying slopes, very negative over here, slightly positive over here. So it's not constant. Agreed? But if you start thinking about the slopes on this one, I think I need to move this graph a tiny bit. Yep, there we go. If you start thinking about the slopes on here, let's start right here at 0. What's the slope right here? 0. So on my y prime graph, y prime, or the y, is going to equal the slopes, which better equal 0 at 0. So the graph of this guy better go through 0, 0. Over here, I don't know what the slope is, but I know it's definitely negative, correct? And then definitely negative, and then definitely negative. Some kids will make a sign line if they struggle. So I want to show you that in case you're ever on the struggle bus with the graphings, either sketching them or matching them. If I was to be graphing y equals f prime and trying to figure out which one it goes with, it better go through at 0, the slope is 0. Over here, although I don't know what they are, they're very negative, and then less so, and then less so, and then less so, and less so. Same here. They're slightly positive and then more positive. Does that make sense? So your y's for this one have to be very negative, approach 0, and then go very positive. The y values. Which graph would go with that? Very negative, and then through 0, and then very positive. D. Now also it helps to know that power rule. I taught it to you ahead of time. It helps with graphing too, because this would have been a quadratic, right? And when it goes down a degree, which it does, because that's what our power rule will do today, it goes to a linear. So any parabola, its derivative graph is always a line. Let's go look at 42 next. I'm saving 41 for a second. 42, what's the graph at 1? Slope? 1, right? What's the slope over here? 1. Slope over here? 1. So if I were to make a sign line for this, at 0 I'm going to go question mark because I can't get a tangent line in there at 0. That actually has a name that we'll give it tomorrow. It's called a cusp. I'm going to put a question mark here, but I sure know everywhere over here y has to equal the slopes, which is going to be 1. Over here, what are the slopes? -1. So over here on my slope graph, remember I'm thinking f prime, it better be 1 to the right of 0 and -1 to the left. Who does it obviously go with? C. All right. The hardest one to interpret is 41. And there's on your homework today, there's 8 of these where you'll match them. None of them are particularly difficult. They're all kind of like this. Again, you're looking at slopes. I'm going to make a sign line where I kind of look at the slopes. Is there anywhere where the slope is 0 on that graph? No. Anywhere the slope's negative? And you're shaking your head, correct? So my sign line, if I were to start right in here where the graph starts, because 0's over here and I can't quite get at it, but isn't the slope right here pretty steep? right? It's positive, positive, less so, less so. And what does it approach? What will the slopes approach eventually? Kind of zero-ish, right? So they're very positive, less positive, less positive, less positive, less positive. So you have to look at y values that start from way up above, very positive, and then get less so and less. They're never negative. So we're always above. Which one does it go with? I mean, it's the last one left, but I want you to understand why. Which one was it? C? A? Thank you. So it goes with A. And you'll have some practice with that in your homework, and then again on Thursday, I think I'm going to put you on the computer to match some stuff up. All right, so that's task number 1. Let's move along. So let's see if, again, from yesterday, we've got these 2 formal definitions for the derivative. This one gives you the slopes anywhere. This one gives you the slopes just at A. All right, and I told you you never have to do it again unless you're not done with yesterday's assignment, but you have to pick it apart. We're only going to pick apart 2 of them. Here, we'll go to letter A here. First of all, let me pick on somebody. I don't have the headset on, but Daniel, it's been a long time for you. Is this one the formal definition or its alternative? Yes, this is the kicker. So that's exactly what it is. This is f of x plus h minus f of x all over h at a specific value for x. Do you want to bail or do you want to answer my next question? Awesome. So if this is the formal definition of the derivative and you have to figure out what the original function was and where it's being evaluated at, that's all you have to do is pick apart somebody else's work. What do you think, Daniel, since you said you're going to keep going, what do you think the original function was if this is f of x plus h minus f of x over h? See, and once he sees it, he'll never unsee it. It's so easy to pick it apart. That must have been the original function, right? But what got shoved in for x? 2. Do you see how that works? One more like that. Let's go to this guy. All right, again, this is the same one as Daniel. It actually is the formal definition of the derivative that works everywhere, but somebody has plugged a 2 in specifically. On this one, f of x plus h minus f of x over h. You ready? Who's the function? It's kind of like a puzzle. What's the function? What do you think? Tangent. Yeah, it's just tan x, whoever said that. It's tangent x, and this was f of x plus h minus f of x. Now be careful. Where are they doing it at? What is the x? Actually, you can see it if I write it like this, f of x plus h. What's the x? You can see it right below it, right? Can't you, Nate? It's pi over 4. So somebody who gets it, tell me where that 1's coming from. Yeah, it is. It's f of x plus h minus f of x, but we're using a pi over 4. What's tangent of pi fourths? 1. Do you see how it works? You pick it apart. We're going to pick apart one more, and then we're moving on. Let's go to C. No, not that kind. I want to go to one that's alternative. Here's an alternative form. What was I looking for, by the way? Just watching me scroll, do you know what I was looking for, Alejandro? Because I said I'm looking for the alternative form. Yeah, x approaching a specific number. Remember the format for that. It's written at the top of your page. This is so easy to figure it out because it's in the form f of x minus f of a over x minus a. So you can't, if you get the format, what's f of x? X minus 1 squared. Yeah, it's easy, right? And what is the constant that we're evaluating it at? 3. Done. All right, so you need to be able to pick them apart. It's way easier than actually doing it. We will bail on that for now because it's coming back at another day. So I really want to make sure you know how to use the power rule at its easiest level so that we can save some time. So yesterday, do you remember what I said we do for the power rule? What did I say we do with the power? Somebody go ahead and tell me. Bring it out front, exactly, Gunnar. So it'd be n times x to the, and then what do I do with the power? I bring it out front, and then I subtract 1. Yeah, so whenever you're doing this, to each term in a polynomial, you just bring the power out front, knock it down. The ones that are super fast are if it's the constant part of the polynomial. So those of you who watched the notes yesterday, what did I say the derivative of any constant is? 0. Who said that? I don't know where it came from. There it is. It's 0. Do you understand why on a graph? Well, the slope is 0. Yeah, constant functions are horizontal lines. That's why. And I also said, let's see if you remember this one, Kellen. I also said what the derivative was of any line. 2x plus 1, 8x minus 7. Those you can just sort of, boom. I won't even power rule them. The power rule works. But these you should just know. What did you say it is? It is. It's the slope of the line. Do you remember why, Christian? You could power rule it. If I said, you know what, here's my function, and if he goes, well, I'm going to power rule this. This would have been x to the first. This would be x to the 0. I bring it out front, and I get 3. Knock it down, x to the 0. The 0 kills this when I bring it out front. Boom. Do you remember graphically why it is the m? That's manually or computationally why it's the m. But why, like kind of what Cullen said, it makes a horizontal line, so the slope's always 0 for that one. Why is the derivative always the slope of the line? Yeah. Yeah, exactly. That's what the derivative is. It's the slope of the tangent line. So if I said, hey, what's the slope of the tangent line right here? Well, the tangent line's the line itself. So, do you get that, Bo? All right, so those are going to make our life easy. We're going to crank off a couple of these. Are you ready? The constants always go to 0, so those you just can kind of, when you take a derivative, you can just kind of in your brain, don't power rule them. You bring the constant out front, and what's the derivative of this single linear term? This would be 6x to the first. What's this guy's derivative going to be? Minus 2, and I'm done. And I don't want you to do them the long way anymore unless you haven't finished yesterday's assignment. Okay? Now, let's go go ahead, how about Elaine? Using the power rule on this, what would you say our derivative is? Yep. Yep. Perfect. Are you comfortable doing that? All right, and we'll get ones that get messier. That's Friday's task. Friday's going to be so easy because our book assumes we haven't talked about the power rule yet. So you have the general concept. I do want to make sure you can work with fractions. So let's go down to this guy because there's one today, I think. When you bring this out front, you'd have a negative times a negative, so you get a positive 3x to the. Make sure when you knock your fraction down, remember you knock it down and you subtract 1. If I were you, I'd disguise 1 as denominator over denominator. Makes it so you won't make any mistakes. So when I subtract 1 from negative a half, what do I have for sure? Negative 3/2. Yep. And then my next one would be plus, bring this out front, 3/2 x to the, then we're going to drop this one disguised as 2/2. X to what power? Negative a half, right? So that's just quick power rule to make our task that we really want to accomplish today go well. So we've got the power rule down. We're not going to do that. We're going to move right on. Here's our big goal today. So take out your calculators. We're going to use them. If I had to say there's somebody asked me, what do you want them to leave here knowing how to do today? I'd say write an equation for a tangent line. So we're going to back up our work on a calculator, and then I'll show you a couple other things your calculator does that maybe you didn't know they do. So first of all, you'll be given a function. And again, we're staying out of our book because our book doesn't introduce the power rule yet, but doing this the long way muddles the issue, and we never will. So I want you guys just to go ahead and tell me what the derivative is right now. What is it? Easy. That just saved us 10 minutes. Okay, that's why I like to introduce the power rule early, because I just really want a function that'll generate my slopes. There it is. The 1 disappears. It's so easy. It makes things nice. What I want you to do is on your calculator, go graph the original function. So let's go make a little grid right here. And let's go in our y1 and graph 3/2 x squared plus 1. You should know what it's going to make, but I want it on your calculator so you can see how you can check your work. Because on your homework, I have you graph the original function. I'll let you get that on there. Maybe once the front row has it all typed in. And you're staring at a parabola opening up. Shouldn't shock you, right? The problem says, so if we go to part B, this is what we've got going so far. The problem says that we're supposed to find an equation for a tangent line at this point. This point's a typo though. So if you go ahead, change this to a 7. If you plug in -2 into our function, we don't get 6, we get 7. I forgot to add 1 to it in the notes. So go over here on your graph and label this. This is a point -2, 7. We have a really easy task today. All I need you to do is give me an equation for the tangent line at this point. Hey Nate, have you ever been asked to give an equation for a line in math?
Yeah.
What do you need?
Slope.
You need the slope. Can you get the slope with just 1 point?
Nope.
Not without calculus. But now your answer is, can you get the slope with just 1 point? Yes, if you can find the derivative, which we just did. So really, this is algebra 1, write an equation for a line. You need a point. I gave you one, so let's go up here. I gave you the point, right? So really, if you stay out of calculus today and just think of algebra, like Nate said, I said, what do you need? He goes, a point. Well, I gave you one, right? And he said the slope. The only difference is that's kind of little kid notation. It's kind of like using 5 divided by 3. How many of you still write it like that? You don't write that anymore, do you? You write 5 over 3. That's kind of what we're doing now with the m. This is kind of little kid notation. We want the slope, which is the derivative at -2. How am I going to find that? Plug it in. I just used the power rule to get it. It says we do 3 times -2, which is -6. Now, Nate, in Algebra 1, once you had the point and you had the slope, what would be the best form of a line to put it into? Standard, slope-intercept, or point-slope? Duh, right? So we are always going to go point-slope here. So what's my equation for the tangent line going to be? Point-slope form. Y minus the y I know is equal to the slope there, now called the derivative there, times x minus the x you know. To be honest, this lesson today is probably easier than pre-calc's lesson, Algebra 2's, and college algebra's lesson, because it's really just calculus attached to equations of lines. So it should be very easy for you. We're going to cruise a little bit. What I want you to do, though, with this line is go and leave it like this, by the way. Don't even manipulate it or anything, because as a reader for the AP test, if a kid writes this, it's correct. If they write it in y equals mx plus b form, a lot of kids make mistakes, and then it's wrong. So you take the last listed answer. So just leave this. However, to enter it on your calculator in y2, go ahead, and you don't need to distribute that -6 in. Just go ahead and enter that in y2, and I want to show you a couple things on your calculator. First of all, it should draw this line. Did it? This line should have 2 properties. It should be at -2, 7. Here's how you make your calculator check that. If you hit second and then the calc button, the first option says value. Do you see that? So go there and give it that x value, and it should pop a bleeper up right there. So you'll be 100% sure. All right? So I'm 100% sure I'm at the right point. And now something I didn't tell you yesterday. Your calculator will take derivatives and slopes anywhere on that curve. Remember yesterday we used Math 8? That's when we had the function. If you have the graph already graphed, hit this. Go second calc, and I bet you're going to guess which one it is. Go read down the list of options that have been programmed into your calculator. Who do you think it is? Go hit second calc. Who do you think is going to give us the slope? Number 6. Yeah, so go second calc, hit number 6. And again, it's going to ask you, it's waiting for you to tell it where to take the slope of the tangent line. So again, hit x equals -2. And it better pop up a -6. We're confirming, do we have the right point of tangency and do we have the right slope? Hit math, not math, second calc. Not math 8, I want you to, there's 2 derivative options on your calculator. One right off the graph. Did you get it to work? Did you get it? One right off the graph, and then yesterday's was if we don't have the graph. All right, so let's flip right onto the next page here. So in a nutshell, how do you get an equation for the tangent line? I'm going to go back to Nate. He didn't even know the calculus of it, but he said you need a point. Here's my point. What if, Bo, I only gave you the x coordinate of the point? Yes. And now I'm going to say, eventually we're going to have 3 functions, f prime, which you already know what that is, a derivative, and we're going to have an f double prime, which actually is called a second derivative. It deals with curvature. In physics, it goes, position is considered f, velocity f prime, acceleration is f double. Do you know what comes after acceleration? Jerk, then jolt, then jounce, then snap, crackle, pop. And I'm not making it up. Those are all the rates at which, all right, so jerk is the rate that acceleration's changing. When you change your acceleration very fast, doesn't your body jerk? You know what I mean? If you're going very fast and all of a sudden, oh, it's like hitting the brakes, correct? So we're going to have these multiple derivatives. So although, Bo, you said plug it in, it's going to be really important when we have 4 functions running to get points, they go into the original function. To get slopes, they go into your derivative. And we'll wait on the other stuff. Are you ready? So find the derivative. Again, Nate said he can't do it without 2 points, and I'm like, with calculus we can. It's no longer the case that you need 2 points to find a slope. You do not. Okay? Next up, calculate the derivative at the x value. The derivative is a function of x. And this is your slope. All right? And then it says use point slope form. So let's make sure you remember your point slope form. We're going to tweak it a little bit. Instead of y2 minus y1, I'm going to call it y minus the y you know is equal to, and instead of m, I said m's old. We won't write m in here anymore, hardly ever. We'll be doing the derivative evaluated, right, at the x value times x minus the x we know. So that it's point slope form though. All right, last one. Super easy. All right, last one up. First of all, go do part A. Should take you 2 seconds because I told you the power rule early. The first year I taught this, I followed the book and I had to give them 10 minutes because they had to do the x plus h stuff and it muddles the issue. Honestly, it should be instant. What's your g prime of x? 2x minus 4, done. What does this give you, Clausen? Slopes, anywhere on the curve. We're going to hop on the curve. Actually, I know it's a parabola that opens up because I understand it, right? We're going to hop on that curve at 3. Okay, so now I'm missing a point and Bo said plug it in. I now have 2 functions. I have a g function and a g prime. What do I plug it into? Thank you. What do you think a lot of kids plug it into? G prime. So you got to be careful. Are you ready? Points, slopes. You up? Are you ready? Clausen, you're up. No, you're just going to say point or slope. Points. Say it again. Come on, Clausen. Slope. Slope. If you're listening to this video, you can't see me clearly pointing to the derivative. Slope. We're playing a game here. I'm going to give you some rhythm. Are you ready? You just have no intercept. You're going to say point or you're going to say slope. Are you ready? No. No. This gives you slopes. This gives you points. Slopes. It's funny, you laugh, but do you think historically in all the years I've taught this, I have students consistently plug their numbers into the wrong functions, especially when we get 3 going, because we're going to be talking about points on the graph. That's f of. We're going to be talking about slopes there. That's f primes of. We're going to be talking about curvature there. That's f double primes of. So that's why we can't use pronouns in here. If you say it's increasing, I don't know, is that f prime, or f double? So again, it's silly. I'm super glad you're making the mistake because it super matters. I want a point. Do I put it in this one or this one? This one's for points on the graph. This one's for slopes. Are you ready? This one's for, thank you, and. Do you think he's got it? Oh, no? Let's add a little rhythm to it and say it louder. You ready? He's got it. All right. So I want the point. So what do I put 3 into, Clausen? This one or this one? Thank you. Go do it. You guys tell me. I don't want to do the arithmetic. I don't do math. I just teach it. Go plug it in. What's our point? 3 comma what? 6. We put it into the point function. We also need the slope there. In this scenario, it'd be called g prime of 3. It's the new m. Correct? Now it's a slope. Where do I put it, Clausen? Here or here? Awesome. See, he'll never forget now. He will never this whole year plug something into the wrong function. Mark my words, because he was publicly humiliated, and it's not fun. All right. He's smiling. You don't hate me, do you? All right. So let's wrap this up. It says write an equation for the tangent line. You'll be writing an equation for this line. Y minus the y I know is equal to the slope there, now called the derivative there, times x minus the x I know, and you leave it. How easy is that? Is that easy, Jake?
Yeah.
You'd be surprised how many people screw it up. Especially if the wording starts to get changed. They say they want the tangent line to run parallel to, and then you got to say, oh, parallel line slopes are the same. But that means derivatives are the same. So I said derivatives equal. So you're going to have to do some interpretation eventually. Last up, Clausen, it's up to you. See if you pick the right one. What value of x is the slope of the graph equal to 6? This one or this one? Thank you. Do you think I have people set the top one equal to 6 or plug 6 into the top one? Yes. So that's why I'm really killing it here. Now the math, I told you the math is easy peasy. All you do is solve that. If you can't solve that, you're voted off the island forever. I don't even want to ask. I'm going to. Jake, what's x?
5.
Yes. See? Oh, so easy. All right. I'm going to shut this recording off, and we're going to pass this up.